If you guess right, you get a positive value for the symbol. If you guess wrong, you get a negative value for the symbol. On the other hand, this smooth wall, if it's not pinned to the wall, not glued to the wall has to push on the lamp. So let's draw the forces in the direction that we know they have to act. It'll lead to less confusion in the end. Also, since point B is directly below point A, let's make it look that way on our free body diagram. Again, it'll avoid confusion as we get around to writing the equations and trying to solve them. You don't have to trace the free body diagram, you don't have to trace the picture, but the closer you can get it to realistic, the easier it's going to be to figure out what's going on and get the equations correct. Summing forces vertically, AY minus W, and we've got a value for W, so I'll go ahead and put it in. 24.525 newtons, sum of forces equals 0. Sum of moments equals 0. Again, I've got three unknowns. Summing moments about A will get rid of AX and AY. Will give me an equation where BX is the only unknown. Actually, summing moments about B would work just as well because the line of action of AY passes through B and has no moment either. So choose a point through which as many unknowns pass as possible. Get rid of as many unknowns from the equation as possible. It'll make the resulting equations easier to solve. If I sum moments about A, get rid of AX and AY, I'm going to have the moment of the weight. Again, I'll take counterclockwise to be positive. So I'm going to have the weight 24.525. Force times perpendicular distance between the line of action of the force and the point that I'm taking moments about. So I need the perpendicular distance, which in this case is 300 millimeters. And that's going to give a counterclockwise or positive rotation around A. BX is going to give a clockwise or negative rotation. Force times perpendicular distance. BX is the only unknown and I can solve for it. So BX is going to come out to be 32 newtons. Well, I should write it out. It's going to be 31.98913 newtons, which for a final answer I'll round off to 32.0. And then AX is equal to BX. And AY is equal to the weight, 24.525 newtons. Or, I guess since these are final answers, I should round that off to either 3 or 4 significant figures, 24.5 newtons. It doesn't matter whether we write the moment as Newton meters or Newton millimeters, as long as we use the same dimensions in each term. When you get into strength of materials and dynamics, you'll have to be a little bit more careful. But for right now, every term has exactly the same types of dimensions equals 0. As long as you keep the dimensions the same in every term, it really doesn't matter what those dimensions are.
Is B directly below A though? Because like there's like 10 millimeter gap between the ball. Did you need to account for that?
In my solution, I did not account for that. I was taking it looks like I should have. I was taking B as directly below the center of the pin, but clearly that's not what the author intended, is it? Okay, so if B is not directly below the center of the pin, where does that come in? Makes no difference in any of the equations, does it? But you're right, I should have recognized that BX the point there is not exactly below the center of the pin. If there had been a vertical force, then that moment would, the vertical force would not have passed through the center of the pin, and I would have had to include it in my moments. But since it was a smooth wall and there was only a horizontal force, I got lucky. I didn't do it right, but I got lucky. Is there another question here? Or? Yes?
Then wouldn't that perpendicular distance to your weight be 310 to 300?
Well, I guess the question is, where do the forces on the pin act? Do they act through the middle of the pin, or do they act at the edge of the pin? And the forces on the pin are going to be created, we're assuming that the pin is smooth, or that it's well oiled, and therefore the forces on the pin, which ultimately create the AX and the AY, are going to pass through the center of the pin. So when I replace all of these forces with the equivalent force couple, and that's what this is, it's an equivalent force couple, those forces are going to act through the center of the pin. So these forces that I've shown, AX and AY, act through the center of the pin, and the moment arm that I need there is going to be the 300, not the 310. So I'm taking moments through the center of the pin, not the wall or the edge of the pin. Yeah, again, this point should have missed the center of the pin by just a little bit, but that distance didn't enter into any of the equations. Actually, there's another part of this problem that it wants to know. It says there is a thumb screw at C, which we can use to adjust that lamp, point it more out or point it more down. And it wants to know what the moment is, what moment is necessary by that thumb screw to prevent the lamp from rotating. So now I need to redraw my free body diagram. I'm trying to find the reaction at that thumb screw, so I've got to separate it and make that reaction visible on my free body diagram. Don't start drawing arrows on here and try to use the same free body diagram from both, because you'll just confuse yourself. So start over, new free body diagram. The weight, which is the same, we ignored the weight of the arm coming out here as being small compared to the other forces in the problem. And then I'm going to have forces CX, CY. The thumb screw has to prevent this thing from moving horizontally and vertically, as well as preventing the lamp from rotating. So I'll put that on as MC. And again, I can take the sum of forces in the X direction equals 0, sum of forces in the Y direction equals 0. Sum of moments about any point. Again, I'll choose a point through which as many unknowns pass as possible. That's going to be C on this free body diagram. Taking counterclockwise is positive. I don't have to draw this moment at C counterclockwise just because I want to use that as positive in my equation. I can draw it the direction that I think it acts. Whatever I do, if I drew it correctly, I get a positive value for the symbol. If I draw it incorrectly, I get a negative value for the symbol. So in this case, summing moments about C, I'm going to have the weight, which is 24.525, times a moment arm of 100 millimeters, minus the moment MC, sum of moments equals 0, so MC is going to be equal to, well, it's going to be 2,452.5 Newton millimeters, or it's going to be 2.4525 Newton meters. And then we'll round it off for our final answer. We'll say MC is 2.45 Newton meters. Summing forces horizontally, there are no force, well, we're going to have Cx equals 0. There are no other horizontal forces beside the Cx. So Cx has to be 0. Cy minus the weight, 24.525 newtons, equals 0. So Cy ends up being equal to the weight, the same as Ay ended up being equal to the weight. But that's really what it is. If you get the free body diagram correct, then everything else falls out pretty easily. On Wednesday, I'd like to do a couple more two-dimensional equilibrium problems for you, and then we'll look at some three-dimensional